Okay, this is Giancoli Physics AP Edition, 7th edition. We are in Chapter 10, Fluids. We're working on problem 23 today, so let's jump in. That problem reads, what fraction of a piece of iron will be submerged when it floats in mercury? So wrap your brain around that one, come up with a plan, pause the video, come back when you're ready. Okay, so compared to some of our dynamics, kinematics, energy type problems, this seems surprisingly devoid of any numbers. However, since we're in chapter 10 and then this particular section of the book, this is right after they talk about Archimedes' principle, so we can focus in on that area. To express what they're asking us for in terms of values, asking what fraction of a piece of iron will be submerged when it floats in mercury. What that translates to is they want to know what portion or volume will be submerged as compared to the total. We're talking about iron versus mercury. As you may know, mercury is a metal with a very low melting point, so it is liquid at room temperature, and it's also very dense. So it's not surprising that iron would float in it. But what do we do with this here? We have a volume versus another volume. We have no volumes here, so this is clearly a ratio issue. And because we're talking about Archimedes' principle, we're concerned with densities. Because the lower density substances will float, the higher density substances will float. Correction, higher density substances will sink. Let's take a look at our definition of density. Mass per unit volume. So since we're looking for volumes or expressions of volumes, we can rearrange any volume to be the mass divided by the density. So this is getting us a little somewhere. When it comes to the volume, let's do the volume total first. That's actually a little easier. When we're talking about the total volume of a piece of iron, an iron bar, that would be the mass of that iron. Again, a number we don't have, but let's just hope that something will cancel. Divided by the density of that iron. Easy enough. In the top, we're talking about the portion that's submerged. Now, we could look at the iron, because that's what they're really talking about. But since we don't have a lot of information to go on, this is where we bring in Archimedes' principle and recognize that the volume that is displaced by the iron, the mercury, has mass and will have a force of gravity exerted on it. In order to displace that mercury out of the way, it will exert a force back on the iron. So when we calculate this volume of the displacement, yes, that's the volume of the iron that's submerged in the mercury, but it also happens to be the volume of the mercury that is pushed out of the way, which allows us to set this equal to the mass of the mercury divided by the density of the mercury. And oh, by the way, as we just said, because of Archimedes' principle, this mass of mercury we're looking at here is actually equal to the mass of the iron, which is why it's holding up the bar to begin with, because the force of gravity acting on both is equal, so that they cancel. So we have the mass of the iron in both terms now, so that will cancel. And we find that the ratio of this volume is going to be the same as the ratio of the density of the iron to the density of the mercury. And those are values we can look for. So if you're working in the Giancoli textbook, you can use table 10-1. Have that over here. Or you can look it up in your textbook or look it up on the internet. Find the density of iron. Right here, iron or steel, 7.8 times 10 to the third. Kilograms per cubic meter. Not that it matters. We're finding a ratio here, so as long as they're in the same units, we'll be fine. And the density of mercury, which is a liquid, as I said, at room temperature, 13.6 times 10 to the third. You can see the density of the mercury is almost, but not quite, twice as much as the density of the iron. We'd expect just over half of the iron to be submerged. We're expecting a number of just over a half. So go ahead and grab your calculators and see what you get. Okay, now just a minor calculator efficiency tip here. Since these are all in 10 to the third kilograms per cubic meters, you can actually cancel all of this, not just the units, but also the times 10 notation, and more quickly calculate this ratio just by dividing 7.8 by 13.6. You'll get the exact same answer. And for me, that worked out to 0.5735. Which we were given no numbers in this problem, so we go with the significant figures off of the table we have. Looks like we're limited to 2. Would make that 0.57 or 57%. Technically, the question asked for a fraction, in which case, if you really wanted a fraction, you call this 57 hundredths. But we have our answer. Ready to move on to the next one.